Hi everyone. In this video we are going to cover section 5.6 titled Integrals Involving Exponential and Logarithmic Functions. So we're going to be obviously using exponentials and logs, but really you can think of this section as another opportunity to practice using U substitution, because most of the problems that we encounter in this section will involve U substitution. All right, so we start off with our rule for integrals of exponentials. And here we have the two rules. If the derivative of e to the x is e to the x, then the antiderivative of e to the x is e to the x plus a constant c. If the base changes, if the base is not e, then we have that natural log of e that is in the denominator. With derivatives, it was times the natural log of a. And we'll run into fewer of these problems, but in case you do, you can still take the antiderivative if the base is not e, but you have to throw the log of that base in the denominator. All right, so let's look at our first example here. We want to find the antiderivative of this function using U substitution. So we are evaluating the integral of x squared e raised to the negative 2x cubed with respect to x, dx. That's just the variable of integration. All right, so how do we do this? What do you need to recognize? Up here in the exponent, negative 2x cubed, is kind of down here in front. Well, its derivative is kind of down there in front. There's a constant that we'll deal with, okay, but that's the thing that we need to start seeing to help us to do the U substitution. Okay, so we're going to say u is equal to negative 2x cubed, and then its derivative, du, exponent comes down, and we get negative 6x raised to the second power, negative 6x squared, dx. So do you see the x squared dx inside of the integral? That's a good thing. That's why this substitution is going to work, and the only thing that we do with the negative 6 is divide by it to throw it on the other side, and I'm going to write that as negative 1/6 du is equal to x squared dx. So we have everything in our integral that we can write now in terms of u. So we make our substitution, and e to the negative 2x squared, there's the first part, e to the u, and then x squared dx is equal to negative 1/6 du. So I can write that as times negative 1/6 du. Now, if you want to bring this negative 1/6 out in this step in front of the integral sign, that would be fine. Like if you get more as you get more comfortable with this, we can make those rearranging do those rearranging steps, kind of simultaneously. So that negative 1/6, the constant factors out. The integral of e to the u, oddly enough, is e to the u plus a constant c. So that integration involved virtually no work after we did the substitution. The substitution, this part, was the challenging part. The integration was the integral of e to the u is e to the u. Done. Okay? So really focus on that U substitution and understanding what's going on there. Now we back substitute. So we write negative 1/6 e raised to the negative 2x cubed plus our constant c, and call it a day with this problem. I'm going to scroll down to the next one, find the antiderivative of this exponential function. So again, we are evaluating the integral of e to the x radical 1 plus e to the x dx. All right, so we have e to the x both under the radical and outside of the radical, and in this one, our grouped expression is going to be what we set u equal to. U equals 1 plus e to the x, not the square root of that. That would make things turn out terrible, okay? Just what's under the radical, because its derivative, the derivative of 1 is 0, the derivative of e to the x is e to the x dx. All right, so we have our 1 plus e to the x, that becomes u, and then e to the x dx, that becomes du. All right, so after we make our substitution, we say this is equal to the integral of, now I could leave that as a radical, but I know what I'm doing. The next step is going to be to integrate, so I want to write this as u to the 1/2 power du. This problem now we actually have to do some work with our antiderivative. This is now u to the 3/2 over 3/2 plus a constant c, and then we'll simplify and back substitute. The 3/2 flips up to the top, 2/3 times 1 plus e to the x, and that is all raised to the 3/2 power plus our constant c. All right, so that is it for that one. Let's do one now involving a definite integral before moving on to logarithms. All right, so in this one, again, we need to make a u substitution. We're going to set u equal to this expression up in the exponent, 1 minus x. Then the derivative of u, du, is equal to, the derivative of 1 is 0. The derivative of negative x is just negative 1 times d, oops, I was going to write du, times dx. All right, so that is our substitution. So let's see. What do I do with the negative sign there? Well, we can just divide both sides by negative 1 and write this as negative du equals dx. Ultimately, what happens when we make our substitution is we factor a negative out in front of that integral. And what's inside is e to the u times du, because the 1 minus x became u, and then the dx became negative du. What do you do with the bounds? Do you remember from the last section? We need to find new bounds. I like to go up here and say that this is equal to, I'm going to take my top bound, u is equal to 1 minus 2, which is negative 1, and my bottom bound, u is equal to 1 minus 1, which is 0. So the 0 is on the bottom, the negative 1 is up top, which may look a little bit strange. You could do one of two things at this point. You could use this negative sign to flip the bounds. That was one of the properties of integrals that we saw in an earlier section. Or you could just keep going through the problem as is, and it will work itself out naturally. So I'm going to keep going rather than flip the bounds over. I'll drop that negative sign down. And now the integral of e to the u is e to the u, evaluated over the bounds from 0 to negative 1. So then we have a negative sign and then a parentheses, top bound minus bottom bound, e to the negative 1 minus e to the 0. And then let's see, this simplifies to, let's not do too many things at once, negative e to the negative 1, I want to write that as 1 over e. That'll look a little bit cleaner. And then e to the 0 is just 1. And then when you distribute the negative, the 1 becomes positive, so I'll write it first. And the 1 over e becomes negative, so I'll write it second. And that is the answer there. We could get this in decimal form, but exact is just a little bit easier to write down. Next up, we have logarithms. You know you love logs. First up, we have the property formulas involving logarithmic functions. The first one, the integral of x to the negative 1 dx, is the log of x. I also would want to put up here with this, the integral of 1 over x dx is equal to the natural log of x. They're the same thing. X to the negative 1 is 1 over x. But I like to recognize personally that the integral of 1 over x is the log of x. If you have any exponent in the denominator other than 1, you need to use the power rule. Okay, so what do I mean by that? Let me scroll up here for a moment. If I have any other exponent, the integral of 1 over x squared dx, or the integral of 1 over x to the 5th power dx, whatever that exponent is in the denominator, right? You need to bring it up with a negative, x to the negative 5 dx, or the integral of x to the negative 2 dx, and then use the power rule, x to the minus 1 over minus 1, or x to the minus 4 over minus 4, plus my constant c, in order to evaluate that. Those you use the power rule. But if you try that with 1 over x, you run into issues because 1 over x is special. It is the natural log when you take the antiderivative. So if I use the power rule on this, integral of 1 over x dx is the integral of x to the negative 1 dx. If you add 1 to your exponent and divide by your new exponent, oops, it shouldn't be an integral anymore, excuse me. I didn't mean to write, well, I meant to write it, but I'm wrong in writing that. So if you take the antiderivative, apply the power rule, you end up with a 0 in the denominator, which is not defined. Okay, so that is where you run into problems. So you don't just like ignore it and keep going and say, hey, it's 1. That would be wrong. So this is incorrect. We need to recognize that the antiderivative of 1 over x is the natural log of x. Then the second one here, this one's kind of interesting. We give it to you in Calc 1 as a formula. And in Calc 2, you will learn where this comes from when you learn integration by parts. If you're lucky enough to take Calc 2 and maybe even have me for Calc 2, you'll learn where this comes from. But for Calc 1, we say it's a formula. Calc 2, you get to learn about it. All right, so the integral of the natural log of x is x log x minus x plus a constant c. And then when we change the base, x over the log of a times the natural log of x minus 1. So these two are really just formulas that you need to apply to whatever problem you're working on. If you encounter one, the one to be most aware of is that 1 over x, because that's when we'll do some u substitutions and throw some u substitutions at you. Okay, so here we go. Find the antiderivative of 1 over x plus 2. So this is the integral of 1 over x plus 2 dx. We're going to make a little u substitution. U is equal to the denominator. U is equal to x plus 2. Du is equal to the derivative of x is 1. The derivative of 2 is 0. So du is just dx. So this integral after the substitution is 1 over u du. And the integral of that is the natural log of x, or of u, excuse me, the natural log of u plus a constant c, and then back substitute ln of x plus 2 plus our constant c. And one thing that I didn't mention up above, but I should say it here and include it here, is that when we evaluate this antiderivative, we need not parentheses like I have here, but vertical lines for the absolute value. It's the natural log of the absolute value of x plus 2. And the reason that that needs to be there is because this function, 1 over x plus 2, x can be positive or negative. That function exists on both sides of the y-axis. Right? So there's areas that we can find when x is positive or when x is negative, but in taking the antiderivative, we have a natural log, and I can only evaluate the natural log of positive things. Okay, so really it's just something you need to remember to do, but it allows for this function to exist on the left side of the x-axis, okay, because natural log does not. Now, moving on to this other example. This looks nasty, but it's not, I promise. Well, you might not like it, but it looks worse than it is. Find the antiderivative of this beast of a function. So the integral of 2x cubed plus 3x over x to the 4th plus 3x squared dx. Whoa, look at all that. All right, so in this problem, it looks worse than it is. Okay, what I want you to notice, x to the 4th, 3x squared, 2x cubed, 3x, this denominator, if you take the derivative of it, you almost get the numerator. And that's what's going to allow this one to be doable. Okay, so what do I mean by that? If I set u equal to the denominator, x to the 4th plus 3x squared, and then take its derivative, 4x cubed plus 6x dx, you almost get the numerator, right? Do you see it yet? 2x cubed plus 3x. If I factor a 2 out of this expression, 2x cubed plus 3x dx. Oh, cool. That's what makes this possible. And how do you recognize that stuff? Well, you do it the more and more problems you see, the more problems you do, the more likely you will be to see that relationship, that connection. Okay, so that's with u substitution. We're looking for something and its derivative. So we have the function in the denominator whose derivative is up in the numerator, or the expression in the denominator whose derivative is up in the numerator. All right, so this 2 over here is going to give us a 1/2 in front of the du. and then 2x cubed plus 3x dx. And so with our substitution, this is equal to u. So we have the integral of 1 over u, and then all the other stuff is equal to 1/2 du. So we get 1/2 the natural log of u plus c, which is 1/2 the natural log of the absolute value of x to the 4th plus 3x squared plus a constant c. And that plus looks like a times, so let me erase that. That should be a plus sign. There we go. And there is our answer. One more quick example where we apply the third of the logarithm formulas that were given. Okay, and we want to take the antiderivative of the log base 2 of x. So the integral of the log base 2 of x dx is equal to, so how do I apply that formula? I'm just going to rewrite everything that it says, except in place of the a, I'm going to write the base of my problem. So this is x divided by the natural log of 2 times the natural log of x minus 1 plus a constant c. So I didn't do any work in this problem. We didn't need any u substitution here. And the work of the problem involved applying the formula, which really the only difference is the base is 2 instead of the formula it being a. All right, so that quick example will close out this section. Work on the homework. Please let me know if you have questions, and thank you very much for listening. Have a wonderful day.